Welcome to YouTube channel scientific underscore math. We are solving a system of linear equations using the iterative method. Okay, so in this lecture we will discuss different iterative methods to solve the system of linear equation. Okay, so the learning objective is we will learn three iterative methods: the Jacobi iterative method, Gauss-Seidel iterative method, and the successive over relaxation iterative method to solve the system of linear equation. Okay, so in this lecture, first we discuss the introduction to the iterative methods, and we will also discuss condition for convergence of the iterative methods. When will the iterative methods will converge toward the solution? Okay, so let's start. Introduction. An iterative strategy can be used to solve a system of linear equations. The procedure is similar to point iteration method for solving a single nonlinear equation. Okay, so we have already one method. I will provide the link in video description. One watch to solve a single nonlinear equation. Okay, so we will here we are discussing uh, the iterative method to solve a linear. So when solving a system of equations in an iterative method, the equations are written explicitly. Okay. So first, what we will do first, we write the system of equations explicitly with each unknown aspect in terms of other unknown. Okay. For example, let me explain how we can write explicitly. Okay, here we have the first equation and how we can write this one as explicitly. Okay. So for example, a11 x1 is equal to, okay, we take all these terms to the right side. Okay, okay, so this one is the explicit form of this equation, and similarly we write this equation and up to an equation. Okay, for example, we have the explicit form of all this equation is this one for x1, x2 and x3. Okay, so this one is the explicit form with each unknown expressed in terms of other unknowns. Each unknown is expressed in terms of unknowns. Each unknown here x2 is with other unknown, xn with other unknown. Okay, so this one is the explicit form. We write the given system of equations in explicit form like that. Okay, so the procedure for solving the system, for solving the problem begins with assuming the initial value or initial values for the unknown. Okay, it's mean when we start solve the system of equations, first we take an estimated solution or the initial values or initial guess. Okay, the first estimated solution or the initial guess is substituted on the right hand side of the equation in the first iteration. For example, this one is the right side, and we will substitute the initial guess or the initial estimated solution of these unknown. Okay, in the first iteration with the new value determined for the unknown becoming the second estimated solution. Okay, so when we after substituting the initial value, and we will get a new estimated solution, and that will be the second uh, that will be the second estimated solution. Okay, so the second solution is replaced back into the equation in the second iteration to obtain the fresh value for the unknown, which is the third estimated solution, and the iteration continue in the same way, and if the procedure is successful, the solution gained through subsequent iteration converge to the final solution. Okay, so we will continue this process until we get our required result. Okay, so for example, a system of an equation, the explicit equation for the xi unknown. Okay, so we have the general form of the n system of equations, explicit equation. Okay, so this one is the a general form for n system of equations, explicit set. General form for n system of equation, n system of equations. Okay, so now we discuss when this iterative method will converge toward the exact solution, or will not converge to the uh, exact solution. Okay, convergence condition for convergence for the iterative method. Okay, so we have a sufficient condition, not a necessary condition. Okay, a sufficient condition for the convergence for a system of any equations like ax is equal to is the absolute value of the diagonal element in each row of the matrix of coefficient A is the total of the absolute values of the of diagonal elements. What does it means, for example, we have a matrix, for example, a11, a12, a13, a21, a22, a23, a31, a32, and a33. Okay, so these are the diagonal elements and these are the off diagonal elements. Okay, so we have the absolute value of the diagonal element should be greater than the total of absolute value of diagonal elements. Total are the sum of diagonal elements. Similarly, for this one, a22 should be greater than a21 plus a23. This is the condition, sufficient condition for the convergence of the iterative methods. Okay, so here we have the general form of this one, and what is this condition when using the iteration approach. This condition is sufficient but not required for convergence. The matrix coefficient A is defined as the strictly diagonally dominant when the above condition is satisfied. Okay, when this condition is satisfied, this means the given matrix is the strictly diagonally dominant. We have already studied about the strictly diagonally dominant matrix, when the matrix is strictly diagonally dominant or not. Okay, so the solution on the other hand could converges even faster. It's mean when the given matrix, when the matrix of coefficient is strictly diagonally dominant, then the iterative method will converge faster toward the exact solution. Okay, so what we even if the matrix is not diagonally dominant, it can converges but not guaranteed. Okay, it's mean the iterative methods can be converges, but we will not guaranteed about it will converges toward the exact solution or not. We will not give any guarantee. Okay, so the we have the iterative methods that are Jacobi method and the Gauss-Seidel method and the successive over relaxation method. Okay, difference between the Jacobi and the Gauss-Seidel method is we have in Jacobi method the estimated value of the unknown are all updated at once at the end of each iteration. Okay, when the first iteration is completed, then we will update the values of the unknown. Okay, But in Gauss-Seidel method, when a new estimate for an unknown is calculated, the value of each unknown is updated. We will update continuously in the same iteration of the values of the unknowns. Okay, the values of the unknowns is updated and is used in the calculation for the new estimate of the rest of the unknowns in the same iteration. Okay, I will also explain when we will solve example related to the Gauss-Seidel method. Okay, so thank you so much for watching my video. Please subscribe my channel scientific underscore math for more updates. In next lecture, we will solve example related to the Jacobi method.